Hello, everyone, and welcome to episode number 16 of The Display Show. I'm Brian Berkeley, your host, here to discuss new developments from the electronic display world. Today's guest is Dr. Eric Virey. Eric serves as Senior Display Market and Technology Analyst at Yole Développement. Prior to that, he drove Yole's LED and sapphire activities. Today, Eric and I discussed mini-LED and especially micro-LED displays. We covered the definition of mini versus micro-LEDs, the importance of micro-LEDs to Apple and their disruptive approach to micro-LED displays, the Cambrian Explosion in technology, including QD-microLEDs and micro-LED display adoption trends and product forecasts. Please don't forget to subscribe and click the bell for notifications when new episodes are released. Now, on with the show. Eric, thanks for joining us today and welcome to the Display Show.
Thanks, Brian. Pleasure to be here.
Micro-LED displays are a hot topic in our industry. There have been lots of prototypes in recent years, as shown here. And on this next graphic, you can see the first commercial products coming to market last year and now in 2022. I should probably also explain that when we talk about mini and micro-LED displays, we are generally referring to displays that use small LEDs to form their subpixels. That means that a mini LED or a micro LED display is different from LCD displays that use LEDs or mini LEDs as their backlight. We'll show a graphic in a moment to explain the difference. Today, we're talking mostly about mini LED displays and especially micro LED displays. These displays, especially micro LED displays, have made a big splash due to their high quality, including fast response time, completely dark black levels, best-in-class angle of view, and other strong performance characteristics. As I just showed, we've begun to see these displays enter the marketplace. And for this specific new category of displays, there are very few people in the world who know more about this field than Eric. So Eric, we're really glad to have you here today.
Thanks, Brian. Thanks for the introduction. I'm really pleased to be here. I've been watching the Display Show since episode 1, and it's already become a cult classic for me.
Well, thank you. Before we dive into the technology, Eric, why don't you tell us a little bit about your company, Yole, and your role there?
Sure. I'm a senior analyst display at Yole Développement, which is a consulting and marketing research company. We cover the semiconductor industry in a broad sense, the traditional microprocessors, memories, etc., but also photonic sensing, display, power and wireless, etc. I think we're usually well known for our off-the-shelf report, but the bulk of the activity is actually consulting projects with different companies. And what's also probably lesser known is that Yole Développement is part of a larger group of companies that has about 150 collaborators. We do all kinds of market researches and technology scouting. We're involved in M&A, due diligence on both the sell side and buy side. We also have our System Plus consulting division, which is quite unusual in the realm of market research companies. They do tear down and reverse engineering, cost simulation, so they can take any device, tear it down to a very, very fine level of details. They can look at a specific component, say a display or a camera sensors, and tell you exactly all the lithography mask level, the materials, etc. So I would say we're probably one of the first market research companies, if not the only one, to have a clean room. And we operate like, I guess, most of the leading market research company. We usually talk to, or we try to talk to every player in the entire supply chain, goes from equipment suppliers, device, OEM, material suppliers, etc. So we conduct many interviews. We go to a lot of trade shows, events every year. We try to be quite visible. And I would say we don't just monitor the industry, we are part of the industry.
Yeah, I know you've been coming to SID for many years in a row, and we certainly appreciate your participation there.
Oh, it's the mecca of display.
The mecca. Now, a moment ago, I was speaking about the difference between LCDs versus mini and micro LED displays. So please give our viewers more explanation, and maybe a graphic will help here.
Sure. So maybe starting from scratch, I don't know how familiar your viewers are intimately with the different display technologies. So the most common one spread is the LCD, and the LCD is what I would call indirect display technology, in a sense that the light the viewer receives comes from a white LED backlight that is positioned at the back of the displays. And that white light goes through a matrix, basically, of very small liquid crystal light switches that can either block the light or let it go through pattern red, green, and blue color filters that constitute the individual subpixels. So what the viewer sees is actually the light that has been growing through all those stacks of material. And this is inherently quite inefficient because say the red color filter is going to filter out the green and the blue, etc. So overall, the overall stack, depending on the technologies, the resolution, typically the overall efficiency of a LCD display is anywhere between 4 to 8%. So compare that to what we call a self-emissive display, and the most well-known example is OLED. In a self-emissive display, every single subpixel is a tiny light source that is individually controllable and emits its own light. So it can be done as represented here using directly red, green, and blue OLEDs, or in today's OLED TV, it's a white OLED that still goes through a pattern color filter. And more recently, we've seen the emergence at Samsung displays and brands like Sony, and hopefully Samsung Electronics later this year will have the first QD-OLED displays, which are potentially much more energy efficient. So I encourage you actually to go back to the previous episode, I think the February episode of the display show, where QD-OLED is discussed extensively.
Yeah, we talked about that in episode number 15.
Okay, perfect. And you can also look at some other videos out there. Jeff Urek has an excellent video explaining in details what is a pixel. But going now more specifically to micro-LEDs. So micro-LED are in a sense quite similar to OLED in the sense that they are self-emissive technologies. The difference is that unlike OLED that can be manufactured over a very large surface, you can deposit the OLED materials directly on what is called the display backplane, the electronic that is going to drive the pixels. You cannot do that with inorganic LEDs. So they have to be manufactured on traditional semiconductor technologies, on small wafers, anywhere from 4-inch to maximum 12-inch. And the art of making a micro-LED display consists then in singulating all those micro-LEDs and assembling them onto the display backplane. And you can do it the way it's shown here, starting from red, green, and blue LED wafers, or you can actually do it starting from just a blue or even UV micro-LEDs and combine them with a pattern quantum dot or color converter layer. So this is in essence very similar to the QD OLED structures, except that the emitter is no longer organic LED, but an inorganic blue LED.
Well, I'm going to want to come back to that image on the right there and talk about color conversion more a little bit later. But I probably should jump in here to explain the difference between micro-LED and micro-OLED displays. Those two sometimes get conflated. But for clarity, as your slide here says, micro-LED displays are comprised of discrete inorganic LEDs. So for completeness, here's an image of a micro-OLED display. My colleague, Amal Ghosh, is the Chief Operating Officer of Imagine, and also he's a past president of SID. These images show Imagine's micro-OLED displays, and it's easiest to think of a micro-OLED display as an OLED display with a very fine pitch, say 2000 ppi or even higher. But micro-OLED composition and fabrication, Eric, as you've just explained, is completely different from micro-LEDs. So going back to your graphic, That's a very good depiction of a micro-LED display. And talking about mini-LED versus micro-LED displays, I'll mention that there is some disagreement or even industry confusion as to what is mini versus what is micro. As just one example, when Samsung introduced the wall display in 2018, they called it a micro-LED display, but I would consider that display to actually be a mini-LED display. And by the way, it's a beautiful display. We used it in the conference room at one of our ICDM standardization meetings. Eric, please help us to understand the dividing line between mini-LED and micro-LED displays.
Yes, indeed, there's a lot of confusion out there because there is no commonly accepted definition of what is a micro-LED, what is a mini-LED. So there's a lot of confusion and a little bit of abuse by some marketing departments in some companies. So the way we look at it, I think most people are familiar with traditional LEDs. They are now really widespread in light bulb, automotive lighting. They're everywhere, and they've been used for a long time actually as the backlight source for LCD displays. Typically, in terms of size, they range from, I would say, the smallest 100, 200 micron up to many square millimeters. Micro-LED are really on the other side of the size spectrum, with sizes as small as a micron or even sub-micron sizes. The application is typically direct emissive displays technologies that we just explained. They typically come without a package. They're assembled directly on the printed circuit board or on the TFT, on the display backplane. So somewhere in between, you have that gray area of mini-LED, which in size, I would say, range in between the micro-LED and the traditional LEDs. And in terms of application, the bulk of the application for mini-LED is actually to be used as an enhanced or supercharged LCD backlight, or as you mentioned, as it was the case in Samsung, the wall display, they can be used to create a direct view LED display similar to the one you might used to see in shopping mall, in stadiums, etc. And this is where the frontier can be a little bit blurred, because if you take one of those mini LED direct view LED display that you see in a shopping mall, if you shrink the die size, if you increase the resolution, and if you manage to take it down to a cost where it becomes a consumer product, then all of a sudden you have a TV. So for this particular application, the frontier is not very clear. But to get there, to get that to the cost of a TV, you would have to shrink the size of the LED down to probably less than 20 or 10 micron, which immediately makes it a micro LED.
So the definition seems to be the die size. The LED die size is the defining line. And where is the wall on this chart?
So yes, indeed, we have the Samsung display here in the mini LED categories. That was the first generation of the wall that was using a 125 by 225 micron size LED. So very typical mini LED size. Since then, Samsung has released their first micro LED TV last year that was using a much smaller die, about 75 to 125. So we're slowly getting into micro LED territories. And this year's generation, the 2022, is going to be using die micro LEDs that are about 30 by 60 micron in size. So now we are officially in micro LED territory.
Well, I think we ought to say that at least the die size has to be less than 100 microns. And my inclination is to believe, for a variety of reasons, that it's going to eventually settle on 50 microns or thereabouts or less to be micro LED. Why don't you take us through some of the other products that are actually shipping today on this chart?
So today, if you want to buy micro LED products, your options are still fairly limited. You can buy one of those Samsung TV. We believe the 110-inch will cost you about $80,000. You can buy also some Vuzix augmented reality glasses. They're more geared toward the enterprise market. But if you're really into augmented realities and technologies, you can purchase them. They're available. And Oppo also recently made available, but in very small quantities and only on the Chinese market. They they released some sort of augmented reality glasses that are also monochromatic. But as of today, those are the two main products, I would say 3 products that you can actually purchase. A lot of companies have already shown very exciting prototypes for automotive displays, transparent displays, smartwatch displays. So we are hoping to see all those coming up in the market over the next few years.
Can you spend a moment to tell us a little more about how we got here, starting with LEDs used in backlights and then moving toward use of LEDs as the actual subpixels?
Sure, yeah. So the first LCD displays were using a fluorescent backlight. Actually, LED really entered the market around 2008, 2009. Now they're 100% market for LCD backlight. So initially, the backlight was just an uniform white source. As the technology developed, we're starting to be able to first adjust at least the intensity of that backlight to adjust to the content of the image, so that a very dark image could have darker, lower dark levels. And then we're starting seeing all kind of dimming technology improving from just one-dimensional edge dimming, where you just adjust the lightning different areas in the displays, to what we call a full array local dimming, where you have a much better resolution and the ability to adjust the brightness of the backlight, and therefore the ability to better control the contrast on the final displays. And the most current and recent generation and best performing is what we call the mini-LED backlight, which is basically a full array local dimming, but with much higher resolution. So you can have tens of thousands and up to 96,000 mini LEDs constituting the backlight. They're divided into different zones, and each of those zones can be turned on, off, or the brightness adjusted to match the content of the final display. So as you increase the number of mini LED or independent zone in a backlight, you're tending toward what is the absolute self-emissive displays, where every single pixel is its own emitting device.
It's very helpful to understand the evolution, how we got here, and also this distinction between mini versus micro. Does this mean that making mini LED displays is relatively easy?
Not that much. If you look at the detail of the design, architectural, and engineering choices that go into a mini LED backlight, there's actually a lot that can be done. You can decide to drive the backlight using different type of technology, active matrix, passive matrix. You can use a traditional printed circuit board substrate, or you can use a glass substrate. If you're using glass substrate, it can be passive, or it can be a TFT display, TFT backlight. You can use different type of TFT. You can use different number of chip size, etc. So there's really a lot of complexity getting into the design of mini LED. And what it comes down in the end is to making the right trade-off or compromises between cost, complexity, and performance. And it is a challenge for OEMs and companies that are designing those backlights to figure out how do they position their product in terms of cost versus performance to try to compete against OLED.
There's a lot of different approaches, and I've seen these both in terms of nominations for the Display Industry Awards, the Display of the Year Awards at SID, but also I've seen them in the paper submissions, and we'll be revealing many of those at the SID Display Week 2022 coming up in May. Can you please explain the cost and performance trade-offs for display makers?
Yeah, as I mentioned, there's a lot of compromises that can be made, or trade-offs that can be made in designing a mini LED displays. And what's happening is, as of today, even if OLED are coming down in cost, and over the last year or so we saw LCD temporarily increase, there's still a very significant gap between the cost of LCD and OLED. And this actually allows the mini LED or LCD designers to come up with different kind of trade-off to address different market segment within that gap. So you can either try to get the best performance possible to really go after OLED. This is typically going to mean higher cost for your mini-LED backlight, but you can get close to OLED contrast, you can get higher brightness, etc. Or you can go after like the more mid-range. And I think there's a card to be played here in mini-LED, because as the cost of OLED comes down, OLED are eager to address the mid-range of the market. Whereas at the same time, this is the bulk of the LCD business. And by combining, say, mini-LED with quantum dots, you can get to a level of performance that maybe will prevent OLED from completely trickling down into the LCD bread and butter market.
I'd like to click up a level to talk about micro LEDs. I guess I want to know about why going to the trouble, considering the cost and manufacturing complexity. What are the benefits of micro LEDs compared to OLED-based displays?
Ultimately, being a self-emissive display is just like OLED. Micro-LED retain all the benefits of OLED, that is the perfect black, good contrast, the fast refresh rate, wide viewing angles, etc. And the ability to make a curved or flexible displays. But on top of that, micro-LED could bring other benefits, such as lower power consumption, which is absolutely critical in mobile devices. The brightness could be much, much higher, and this is important. Could be important in TVs, and also in mobile displays for outdoor sun readabilities. But it's also extremely important for augmented reality devices, where for a lot of reasons you need a lot of brightness. You need a very bright displays. We're talking brightness of hundreds of thousands, if not millions of nits that are required for those augmented reality glasses to be able to compete with the outdoor, with the real world direct view of the sun, etc. Other potential benefits of micro-LEDs that are interested for different industry are the ruggedness and the ability of micro-LED to operate over a wide range of temperature. They're also not sensitive to oxygen, moisture, etc. So you don't need to deploy like complex and expensive encapsulation technologies to protect your inorganic LEDs. So this is potentially significant benefits, and the automakers like the potential high brightness, ruggedness of micro-LEDs. They're also intrinsically, because of their design, where you assemble those micro-LEDs onto the backplane, you can also imagine assembling at the same time all kind of micro ICs that could be sensors, drivers, etc. And this opens the door to the ability of inserting all kind of sensors. I'm talking fingerprint, cameras, gesture sensing, etc., within the front plane of the displays. And finally, there's actually unique capabilities of micro-LED, which is the ability to create very large displays by seamlessly tiling smaller modules. And if you look at the current micro-LED TVs that's available this year from Samsung, this is how it's made. The 89-inch is actually a collection of 49 modules that are about 12.7 inch each, that are assembled seamlessly. And the seamless aspect is very important, because you cannot do that with OLED or LCD, simply because the LCD, you need a seal to keep your liquid crystal in place. And with OLED, you need a little bit of room on the edge of the display for that encapsulation that protects the organic materials. So with micro-LED, there's no need for that, and you can really create a seamless displays. I'm not saying it's easy. If you were looking very closely at the first generation of those micro-LED TVs, if you knew what you were looking for, it was fairly easy to spot those seams. And of course, this is unacceptable for consumer displays. I have to give credit to Samsung that I was quite impressed this year at CES by their newest generation of micro-LED TVs. No matter how hard I was trying, I couldn't find any sign of the seams between the tiles. So it seems like we are getting there.
Well, there is surely a lot of interest in LED-based displays, especially the micro-LED displays. In our work on the SID program committee, I just mentioned that a moment ago, but over the past few years, we've seen a surge in the submission of papers on micro-LED developments. And I think you had a chart showing the growth in patents over recent years.
Yeah, absolutely. So I'm like you. I'm really excited. First, I want to say I'm really excited to be back to Display Week in person this year. And just like you, I've seen the micro-LED aspect growing from just like a small session in a small room to almost a conference within the conference. So it's challenging to, when we talk about micro-LED, we are talking about the technologies that doesn't exist yet, in the sense that there is no high volume consumer product. So we can't try to quantify the market by looking at sales and volumes. So a good proxy in that case is to look at the intellectual property activity. And we've been doing that since 2016 with Yole and some partner companies. And what you can see here is the number of micro-LED display patents that have been filed over the past 2 decades. And you can really see that exponential growth, especially since Apple acquired micro-LED startup LuxView in 2014. So you see this exponential growth, and you can see that it's driven mostly by display makers, traditional display makers. A lot of them were a little bit late to start. I think micro-LEDs was maybe falling too far from home in terms of the core technology it involves, or maybe they didn't see the threat, at least until Apple showed interest into it. But since around 2018, as you can see, there's a very, very strong intake of micro-LED patents coming from traditional display companies. And by that, I mean, of course, the LG, Samsung, the BOE, CSOT, Tianma, AUO, Innolux, etc. So I would say now everybody is in the game.
You know, that's quite a hockey stick when you look at the sudden explosion in the number of patent applications. And I appreciate your sharing that slide with us today. And by the way, we're going to talk a little bit more about Apple. I'm going to ask you about that in a moment. While everybody is excited, especially about the potential for micro-LEDs, there are also some very significant challenges toward their mass deployment. And so, Eric, I'd appreciate if you could give us an overview of the primary challenges for micro-LED displays.
Yes, so it's definitely not a slam dunk. And there's a lot of technology bricks that needs to come together, and there's still a lot of challenges. We're talking about the LED efficiency and their cost, the mass transfer, which is probably, at least at first glance, the single largest challenge for micro-LEDs. And there's a lot of technology issues, color conversion, light extraction. How do you drive those micro-LEDs? They're different from OLEDs. The yield and defect management is also, I would say, as of today, is probably one of the single largest remaining challenge for micro-LEDs. So there's a lot that still needs to be done. And we've seen a lot of great prototypes over the year, but there's still a lot of work to be done to iron out the latest details.
Well, let's start with the die transfer and assembly. And Eric, as you pointed out earlier, LEDs are not fabricated directly onto a backplane in the way that active matrix transistors can be fabricated onto the backplane. And therefore, the LEDs are fabricated in a MOCVD reactor, or what they call metal organic chemical vapor deposition, which is a special type of epitaxy process. And then the dies have to be transferred, mass transferred, and assembled onto the substrate. So that's the genesis of this mass transfer requirement So can you tell us about the challenges for mass transfer and assembly?
Absolutely. So it's, as you just said, you can have literally hundreds of millions of micro-LEDs on a single wafer, and you need to somehow transfer that and assemble and do a mechanical and electrical connection to the display backplane. So to put that in perspective, if you're trying to make, say, a 8K TV, it means assembling 100 million micro-LEDs that are the size of a bacteria with an accuracy of about +1 minus micron. And for cost reason, you want to be able to do that in less than 10 minutes. So if you were to use existing semiconductor pick and place equipment, there are tools that just come, pick up a component from a wafer and put it on the substrate where it's supposed to be. If you were to use some of those standard equipment today, it would take about 10 years to assemble a single TV. So there's definitely a need for new transfer and assembly technologies that are really highly disruptive in terms of their throughput. We are talking about 5 orders of magnitude differences. To be honest, when I first started getting interested in micro-LEDs and I started understanding that challenge, I was thinking, okay, I need to move to a different industry. This is not going to work. But then we started looking at patents, talking to a lot of people, and I was really stunned by the amount of creativity that people, scientists and engineers were coming up with to solve this problem. And it started to become more and more realistic. So there are a lot of technologies or processes that could potentially allow you to do that. The most, at a high level, the two major family are what I call the deterministic stamp printing, which in essence is a typical pick and place, except that rather than moving one die at a time, you move a stamp that can pick up thousands, hundreds of thousands of die at a time. So we have a video from one of the pioneering companies in that field, Print, which shows that. So you can see on that video the stamp picking up, say, red micro-LED from the donor wafer, assembling them on a backplane, and then repeating the operation with the blue. And then, of course, you can imagine doing the same thing with the green. You can also imagine bringing up some sensors, micro drivers, etc. So that's what I call deterministic stamp printing, in the sense that the position of the micro-LED is never lost. Per position, you have what I call the self-assembly, and in this case, a fluidic self-assembly. So here, the micro-LEDs are harvested from the wafer. They're detached from the wafers and literally like thrown in bulk into a fluid without any order organization. And then the art of fluidic self-assembly consists in flowing those micro-LED, as you can see on this video from Helix, flowing those micro-LEDs above the display backplane, which features some capture wells. And by a combination of capture wells, shape, and usually some external forces such as electromagnetic, electrostatic forces, you can end up positioning every single micro-LED in its own well. And it's done in a very massively parallel fashion.
This one kind of reminds me of a company called Alien. I don't know if you are familiar, but
Absolutely.
It seems like they were
Yes.
trying something very similar to this many years ago.
Yeah, so Alien technology definitely, in my opinion, pioneered this self-assembly. I think what they were looking at initially was some RFID technologies, but they really have a lot of seminal patents in this field. And when you look specifically at the display area, Helix is probably the one that has been championing this approach. But interestingly, it seems like for a couple of years, fluidic self-assembly went a little bit out of fashion. People started thinking, maybe it's going to be difficult for very small LEDs, etc. And then all of a sudden, at least in terms of intellectual property, we saw a very strong comeback of interest for fluidic self-assembly, including from some of the leading display makers, which are right now filing a lot of patents on different types of self-assembly. So definitely something to keep an eye on.
I've got probably dozens of other questions on this. For instance, they're LEDs, so they have to be in the right orientation. But we don't have to get into all of that right now. I find that an interesting approach as well. What about laser mass transfer approach?
Yes, if you look at the variety of transfer technologies, they can be organized at a high level, as I just showed, by process types. But then, depending on the process, there are different forces that are used to pick up the die, different mechanisms that are used to hold them in place, different mechanisms to release the die. And one technology that's definitely gathered a lot of buzz and excitement over the past 2-3 years are laser-based transfers. So here, the laser is really here to detach the die. And one of the key benefits of laser is the ability to operate selectively. So say you have a donor wafers with millions of micro-LEDs. With a laser, you can selectively which one are going to be transferred. And for a lot of reasons, including yield management, this could be a very key capabilities. So we're seeing more and more laser transfer process. We have some off-the-shelf laser equipment that are available now. I remember that the company, micro-LED startup Glow, really pioneered this field in a sense that, to my knowledge, they were the first to publicly demo full color RGB micro-LED displays that was assembled using a laser-based technology.
Well, that's a good nod to our sponsor, because last year Nanosys acquired Glow, so I appreciate your mentioning them.
Absolutely.
But there are some big challenges here, and it seems like it's this race to find the best technology for manufacturing yield and throughput. And it also seems that the approach taken could depend on the specific application area. What are some of the other challenge areas and trends in this field?
Yeah, so as we mentioned before, there's a lot of major thrust areas where there are still a lot of challenges for micro-LEDs. So we've classified, organized those in different technology blocks, and so we discussed the transfer and assembly. I think we are reaching kind of a turning point with transfer and assembly. There's been so much progress accomplished over the last 3-4 years specifically, and we are now seeing some equipments, off-the-shelf equipments that are available to any company. So it used to be that micro-LED or a company wanting to do micro-LED displays would have to develop their own mass transfer process and develop the equipment, etc. So now they can actually purchase off-the-shelf equipment from reliable and established equipment makers. So this is clearly going to accelerate the development cycles. And some of those tools are, I would say, already good for a first product. They might not be the tools that will be used for mass manufacturing of high volume consumer products, but they can already allow you to do a lot of things. So we are reaching the stage where I think that transfer and assembly is no longer seen as a major roadblock. I don't think we're going to look back 5-10 years from now and say micro-LED failed because of mass transfer. We are not there yet, but there's a clearer runway now. That said, there's still a lot of challenges in terms of the details and the pixel display architecture. I mean, going from a prototypes where all the pixels light up and look okay to something that is absolutely perfect, reliable, with absolutely no visible defect is a long stretch. So you need to work on your pixel structure, on the driving, on the die structure. And I mentioned earlier, I think that the yield management is probably currently the single largest remaining challenge. But no, Overall, what's really impressive is, again, the amount of creativity that the companies, the people involved in this technology are bringing in. So for every challenge, it seems like there's like 5 different potential solutions that are coming up. We're still in what I like to call a Cambrian Explosion phases, where we are not really yet seeing a convergence or standardization of the process. Everybody's trying multiple things. If you look even at mass transfer, the big companies, they're looking at 5, 6 different mass transfers technology. So we're, I think, at a level where we can expect to have more and more consumer product soon, but there's still a lot of work. And in the end, I would say micro-LED is no longer a science project, but it's a gigantic engineering and manufacturing project.
Well, and there are many prototypes and products now even on the marketplace that bear testimony to that. You had mentioned Apple, so I want to go back to that. It's been well reported that Apple is working on micro-LED displays. So without revealing anything in confidence here, can you say which approach they are taking?
Yes, so really based on our thorough analysis of the intellectual property landscape, we're pretty confident that we understand at least some of the key elements of design in Apple's approach. And I would say one of the most disruptive is probably the use of those micro driver ICs. So in typical display, be there LCD or OLED, the display is driven by what is called the backplane, which is a thin film transistor, TFT based technologies. And those thin film transistors backplane, they're manufactured by the big ones in display industries, the Samsung, LG, BOE, CSOT, AO, etc. It's fairly vertically organized and concentrated because it's very capex intensive. Nowadays, a new generation OLED or even large LCD fab, you're talking $5-7 billion. The Apple approach here is to get away with the TFT and use those micro drivers, which are basically very small silicon CMOS micro electronic components that are assembled directly on the front plane, the same way the micro LED are assembled using a mass transfer. And every single of those micro driver IC can drive, we don't know, either a couple of pixels or a block of, who knows, 16, 32 pixels. And on top of the pixel, they can also drive sensors or whatever Apple will decide to insert. So I think it's fairly disruptive in terms of the technologies. It's disruptive in terms of the capabilities that the display will have, because they will be able to integrate all kinds of sensors within the displays. And it's also disruptive in terms of supply chain, because all of a sudden you don't need the big display makers to make your own display. You can purchase or contract the substrate. You have any of the silicon foundry make the microdriver IC. You can do the assembly yourself or not. But by adopting this approach, Apple can potentially disrupt the display supply chain.
What products do you think they're targeting first for micro LED displays? And what will be better about the displays in those products?
Mm-hmm. So we're pretty convinced that initially the first product will be the smartwatch. We're expecting to see a micro LED smartwatch as early as 2024. I think the key benefits would be, so first, in terms of the visual aspect, the display should be at least as good as the best OLED on the market. But we also expect it to be brighter, which will improve outdoor readability and visibility. And we believe that Apple will have the ability to combine these displays, as we just described, with all kinds of sensing technologies. Could be a fingerprint reader, could be gesture sensing, could be also local brightness adjustment. Imagine you have a sun ray hitting the important part of your smartwatch where you only see your heartbeat and you can't read it because of the sun. Then that particular area could become brighter instantaneously. I'm just reflecting here on the many patents that Apple has filed on this technology. It's hard to tell exactly what they're going to be doing, but I'm confident that they will come up with something that will wow the users, or else they won't do it.
It certainly seems like, based on the patent count and their acquisition of LuxView and other public information, that they've got a great deal of interest in this area. There are so many different approaches being investigated and pursued. And as an example of the different directions, even within Samsung Group, there are differences in the approach being taken, for instance, by Samsung Visual Display, who makes the finished displays, and by Samsung Display, who makes the display panels.
Exactly. So Samsung is a good example of that complexity I mentioned earlier, and the multiplicity of approaches that you have. So as you just say, Samsung Visual Displays, which is the company that basically makes the final TV and commercialize them to the consumer. Samsung Visual Display has been developing their own technologies. They invested in a very prominent micro-LED startup called PlayNitride. And with their help, they've developed those mass transfer technologies, dye technologies that are used in the currently available micro-LED TV, the 2022 models. So it's a mass transfer technology using red, green, and blue dye. But then Samsung Electronics, the parent company, is betting on multiple horses, because you have Samsung Display Corporation, the company that makes the LCD panels or OLED panels that go into many smartphones, including Apple smartphones, for example. Samsung Display is developing an entirely different micro-LED technology. It's based on nanorod LEDs, so very small. They're assembled by I would call it a self-assembly technology using inkjet printing. And they're using quantum dot color conversion. So without going into the details of this structure, it's essentially a QD-OLED structure. So I once again refer you to the February episode of the Display Show to understand this structure. And now imagine you take the QD-OLED displays and you just replace the organic LED blue by an inorganic micro-LED. And then you have the micro-LED approach at Samsung Display.
Well, I really want to come back to that in a moment. But first, let's talk about cost. It's highly unlikely that many consumers are going to purchase a TV that costs on the order of $80,000. But as you pointed out, we've literally seen such a model ship recently. Please talk about yield and productivity improvements that are going to drive cost reduction and therefore consumer acceptance in this display category.
Yeah, clearly. So I don't think a lot of us will be able to afford that $80,000 TV, no matter how good it looks. So there's definitely a need for micro-LED, and today this is clearly the single largest obstacle to massive adoption. There's a need to dramatically reduce cost. I'm not taking by 2 times or 5 times. We're talking 10, 20, 50 times, depending on the application. So we looked at the history of LCD, and what you can see is that the cost and price of LCD displays has dropped about 300 times in 25 years. Of course, initially LCD was pretty much a greenfield technology, so everything had to be invented. The processes, the material, the equipment. So when you're such an early stage, of course, there are a lot of low-hanging fruits that can be harvested quickly. But once all those were harvested, LCD mostly achieved the cost reduction through generation scaling, using larger and larger substrates, to the point that now in generation 10, 10.5, fab, you can actually build 6 75-inch on a single glass plate or 8 65-inch. MicroLED, the situation is different because MicroLED exists at the intersection of multiple industries and technologies that are already quite mature. I'm referring here to semiconductor technologies, the LED industry, the existing TFT display industries, photonics, etc. So there's a lot of technology bricks for MicroLED that are already here and available. They just need to be seamlessly plugged in together, maybe re-engineered for MicroLEDs. But what that means is that, of course, because all those technology bricks are already mature, there is maybe no opportunities for a 300 cost reduction global. But it also means that a lot of the opportunities are already here and they just need to be harvested. Which means that we can expect cost reduction fairly quickly. So just giving some example, just the die size, the size of the LED. You mentioned, Brian, at the beginning of our conversation that you believe that ultimately to be successful, micro-LED will have to be way below 50 micron, and that's absolutely right. And the main reason is cost. Today, the die, the micro-LED itself, is probably the single largest contributor of the cost structure of a micro-LED displays, and its cost just scale with the size. So we can imagine if you go from a micro-LED that is 100 by 100 micron to a micro-LED that is 5 by 5 micron, you've already saved orders of magnitude in cost. And the same goes for yield and repair, the transfer and assembly, etc. I'm not saying it's a slam dunk. It's not easy. There's a lot of challenge, but achieving a 20x, 30, 40x cost reduction is doable. We've done it on spreadsheets. Now the question is, how does it translate in real life? But based on the current level of interest we see in micro-LED, I would assume that a lot of display makers have similar spreadsheets to ours.
Along those lines, Analyst is sponsoring these talks, so I feel compelled to go back to a point that we just touched on and that you had touched upon earlier as well. It seems that color conversion technology through quantum dots or some other technology could simplify the manufacturing of micro-LED displays and improve their performance. For one thing, instead of having to deal with separate kinds of LEDs for each of red, green, and blue, it would be simpler to only have to handle a single type of LED, namely blue only. Another point is that green LEDs and especially red micro-LEDs have efficiency issues that could be solved by using only blue LEDs and then apply color conversion. Can you elaborate on quantum efficiency and the potential for using blue micro-LEDs with color conversion?
Yes, indeed. So one of the key promises of micro-LED is efficiency and ultimately the potential for drawing much less on the battery for mobile displays. And if you look at traditional LED, they are indeed much more efficient than OLED. And I'm talking by traditional LED, I'm talking about larger size LED, more than 100 micron and up to millimeter size. So if you look at what's called the external quantum efficiencies of LEDs versus OLED, you're way higher for every single color. The challenge with micro-LEDs is that as you start decreasing the size, the efficiency comes down. I won't go into the details, but this has to do with the manufacturing processes mainly and the harsh etching processes that are required to manufacture those micro-LED, which damage the edges. Yeah, so this loss of efficiency with smaller size is not intrinsic to micro-LED. It's mostly, as of today, a manufacturing and process challenge, but it's not an easy one. And the result is that the smaller the micro-LED go, the less efficient they are. And as we just said, those micro-LEDs, they need to be very small to be cost competitive with other technologies. So if you look at this chart, you see that when you are around 5 micron micro-LEDs, the blue is still more efficient than OLED, but the green and especially the red are actually pretty bad compared to OLED. So you would say, okay, maybe the red is bad, but the blue is so good. that it will make it up. Unfortunately, if you look at the power distribution, optical power distribution in terms of wavelengths, the blue doesn't contribute much to the image. It's typically about 10 to 15% of the power. So long story short, you cannot really make an efficient display if you don't have an efficient red and an efficient green.
These are very interesting charts. I want to point out something that is very important for our viewers to consider. Most folks are thinking that blue is less efficient than red or green. And for OLEDs, that's true. But the reason is because red and green triplet state phosphorescent emitters have existed for many years now for OLEDs, but still not for blue OLED. So you have to think in an exact opposite way when you're talking about micro LEDs, because the blue micro LEDs are very efficient, and yet, as you pointed out, and it was even showing there on your chart, Eric, especially as you shrink the size of the red micro LED in particular, so much of the edges don't emit, and you lose efficiency from the red dye. And so if you were to apply a blue LED with red color conversion and green color conversion, you could boost the efficiency substantially. So this is a very important point. Please continue.
Yes, indeed. As you just say, you can literally harvest the relatively high efficiency of blue micro LED, and by combining it with a red quantum dot converter, you can end up with a very high efficiency red micro LED. This is definitely what Nanosys is doing, and now that they've acquired glow micro LED companies, they have all the technologies in their toolbox. They have a good native red, or they can make a very good color converted red.
So with all of this information, where do we stand on current adoption of this technology?
Yeah, so in terms of adoption, so we've seen many companies now showing prototypes of micro LED displays, and for a very broad range of applications that covers automotive, TVs, augmented reality, smartphones, smartwatches, etc. Today, most companies are still at the stage of prototypes. I think a lot of companies initially underestimated the amount of effort you need to go from a prototype that works well enough to the perfect consumer display. So we might be in one of those, 20-80% conundrum where 20% of the work got you to 80% of the results. You think you're very close to the finish line, but there's much more that needs to be accomplished. Some companies are already there, so we're seeing the first commercial product. We've seen earlier all kind of prototypes coming up. So I think we're getting close to an inflection point. One of the key drivers, something that we are looking closely at, is how successful or not Apple will be with their micro-LED endeavor. If really they succeed with releasing a micro-LED display smartwatch that really is highly differentiating and wows the users around 2024, you can be sure that's going to be a jolt for the industry and accelerate development even further. But even without waiting for that, I think we've somehow reach escape velocity for micro-LED. For many years, we were in a situation where a lot of people were interested in looking at it, but probably not putting the amount of efforts that would have been required to take off. So there were limited resources, which means that equipment makers were staying on the fence, not sure they should invest the time and money to develop equipment, and because there was no off-the-shelf equipment, it would slow down development, etc. I think now that we've break through that vicious circle, and we're seeing more and more people, more and more resources. Apple itself probably spent already more than $2 billion on their micro-LED program. So more money, more people, acceleration of development cycles. So this makes me more optimistic now than I was just a couple of years ago about the prospect of micro-LED.
In your view, what technological approach or approaches will ultimately get the broadest adoption?
So you've heard me say a lot now that there are, for every single technological node and challenge, there are multiple approaches that are being investigated. So we talked about different technologies for mass transfers. For the colors, we talk about color conversion versus native colors. I'm not yet seeing convergence. There's still like an explosion of processes and technologies that say it will unavoidably happen. We're going to see the industry without the worst technological solution, and we're going to start seeing some level of convergence. But ultimately, I think we're still going to see a lot of technology coexist. Color conversion might be more suitable for certain applications than others. Certain type of driving, TFT versus micro drivers, might depend on applications, etc. In the end, it's not that different from, say, OLED, where you can see you have RGB OLED deposited by FMM metal mask. You have white OLED, you have QD OLED. In the near future, we will have inkjet printed OLEDs. So all those coexist depending on which applications and performance you're trying to address. And I think the same will be true for micro-LED.
Does Yole have any forecasts on micro-LED adoption?
Yes, so we do in our off-the-shelf report, we forecast per application in terms of volumes, number of displays, etc. It's always challenging to forecast a technology that doesn't exist yet. So the way we work is we work by scenarios. So we have a basic, conservative, and aggressive scenario, and in our reports we explain in great details what is the roadmap and what are the triggers, the technology, market, supply chain, gateways that are here to enable or to stop one scenario versus the others. But overall, we're quite optimistic now on certain applications. I think augmented reality could be one of the killer applications for micro-LEDs. We're already seeing some products. We are not there yet. One of the major challenges for micro-LED is and will be to have a full color displays. But if this can be done, and there are a lot of technologies that are being investigated to do that, we believe that micro-LED really is a technology that can offer the right combination of cost, brightness, power consumption, and form factor for augmented reality applications. We're also pretty hopeful with a smartwatch, providing Apple is successful with their endeavor. Automotive is also an interesting one because micro-LEDs are bright, rugged, high contrast. They can operate over a wide range of temperature. They last long. So what's not to love for an automakers? So the challenge now is still, of course, the cost and availability. But we believe that automotive could ultimately be one of the killer apps for micro-LEDs.
Well, that's an exploding field by itself.
Yes, yeah. No, and there's definitely enough money to be made there that some display makers that are interested in micro-LEDs are, at least for now, focusing exclusively on automotive. So for other consumer markets, there's still a lot of questions that remains to be addressed. We believe the smartphone is probably the most difficult and challenging application for the simple reason that OLED is already doing an incredible job in terms of performance and price. So because OLED are already so good, it forces micro-LED to go push further into its limit in terms of cost and price. So we believe that Apple will use the smartwatch as a beachhead to kind of test first the acceptance from the consumer, but also stress test their supply chain process, etc. And if everything goes well, maybe 3 years, 4 years after the smartwatch, we might see a smartphone. For TV, it's different. I think we are going to see Samsung already has a TV on the market. It's pretty expensive, but if you look at in terms of dollar per pixel, for example, it's already 40% cheaper than last year's model. So if they can continue down that cost reduction road, we might see some TV competing really only on the high tier of the markets. They're going to compete with the best OLED. They are not going to compete with LCD. But maybe by 25, 26, we might see micro-LED TVs in the, say, $10,000 range, which definitely not a mass market, but starts being a significant consumer market.
Well, it's all very exciting, and it's a rapidly emerging new display technology. Eric, this is most of what I had hoped to cover today. I'd just like to know if you would like to add anything. For instance, where can viewers go to get more information about micro and mini LED displays?
Well, I encourage your viewers to check our website, w3imicronews.com. iMicronews is the media newsletter. You can subscribe for free to our newsletter, and you can meet us at most industry events, conference, trade shows, etc. And when we present at those events, our presentations are usually made available on the website. So this is a good starting point, and of course, don't hesitate to reach out and contact us.
Well, I hope to see you at Display Week 2022 in San Jose in May. Eric, it's been great to talk with you today. Thanks for being our guest.
Thanks a lot for the opportunity, and hope we talk again soon. Thank you.
That's all for today, folks. Please don't forget to subscribe and click the bell for notifications when new episodes are released.